Okay, banked curves with friction. These are some of the messiest things we're going to see all year. So we just did banked curves with no friction. Those were fairly simple. Again, they were pretty much the same thing as something hanging from a string and turning around on an angle and making a horizontal circle. Banked curves with frictions are nothing like that. So anytime you've got a banked curve, just a refresher, you're going to have an angle and you're looking at the back of the car. Center is going to be over here. And when you draw those force diagrams, you need to break apart the normal force so that it's in the same direction as the center. We're going to look at two possibilities for banked curves with friction. First one's going to be banked curves with friction to keep the car from sliding up the curve, and the second one's going to be to keep the car from sliding down the curve. So in other words, a maximum speed and a minimum speed. Let's start with the minimum speed. Let's start with looking at a banked curve, and we're going to be looking at the minimum speed. So what the minimum speed does with banked curves, you have your car, here's the angle, here's the car. Minimum speed keeps the car from sliding down the incline. Let's draw this force diagram, and I'm going to make this pretty big so that we can see how all these angles are working. We have weight Fg going straight down. We have the normal force perpendicular to the surface. If my car wants to slide down the incline, then we need a frictional force to go up the incline. Center is over here, so directly left, which means that we need to break apart Fn and Ff, unlike our old incline problems where we wanted to break apart Fg. Again, the reason we do this is because centripetal force is directed towards the center, so we need our sum of the forces, our net force, to be in the direction of the center of the circle. So breaking apart Fn, we get Fny and Fnx. And you'll remember when we were dealing with no friction, this angle was theta. And then breaking apart Ff, we get Ffx and Ffy. This angle right here, let's take a look at that. So here's my incline. So just kind of mirroring the picture. This angle was phi, which meant that this was theta, this is phi, that was theta, phi, theta, phi. I know that's a lot of thetas and phis. However, what's important for this right here is that Fnx is equal to Fn cosine theta, Fny equals Fn sine theta. That's because theta is the angle relative to the x-axis and the normal force. And then we look at the frictional force. It's phi. So Ffx is equal to frictional force cosine of phi, and Ffy is equal to the frictional force times the sine of phi. The easiest way I can think to remember that phi goes with friction is they both have the f sound. So frictional force, you're using the angle phi, normal force, you're using theta. And again, the reason for that, here's your x-axis. The angle between the frictional force and the component, so the frictional force and the component, which is on the x-axis, is phi. The angle between the normal force and its component is theta. So the angle relative to the x-axis for normal force is theta. The angle relative to the x-axis for frictional force is phi. So friction phi. So in other words, instead of only using one of the angles, we're going to have to use both when it comes to banked curves. So phi with friction, theta with normal force. And this is for minimum speed. Okay, here we go. So looking for the minimum speed, you're going to have friction opposing the direction that the car wants to move going up the incline. This force diagram is an absolute mess. Let's redraw it. So we've got, and I'm just going to redraw it with the components. Going down we have FG. Going up we have FNY and FF. Those two at FFY, those two added together equal FG. Going to the right we had frictional force in the X, and going to the left we had FNX, the normal force X component. We know that the acceleration is in the direction of the center of the circle. Again, center is over here. So my centripetal force equals right minus left, FFX minus FNX. And the centripetal force points to the left, so it has to be negative. In the y direction, top equals bottom because there's no acceleration that way. FNY plus FFY equals FG. Let's jump right in. So in the x direction, negative FC is equal to right minus left. So this is frictional force, x component is times the cosine of phi, minus the normal force, which was on the left. This is Fn cosine theta. To make life easier with negatives as we get towards the end, I'm just going to rearrange this a little bit, switching sides. So centripetal force will equal Fn cosine theta minus FF cosine phi. It just gets rid of one of the negatives, so all I did really was bring this over here and these over there, and that changed the signs. So my centripetal force equals Fn cosine theta minus frictional force cosine of phi. We know that frictional force equals mu Fn, so this becomes Fc equals Fn cosine theta minus mu Fn cosine phi. And then I'm just going to factor out Fn. Fc equals Fn cosine theta minus mu cosine phi. Fc over cosine theta minus mu cosine phi equals Fn. Why did I do that? I'm going to do the same thing in the y direction. So I'm going to isolate Fn, and I'm going to end up setting the two normal force equations equal to each other. Eventually what we're going to get is an equation to solve for either radius, theta, phi, or speed for a car or anything going around a banked curve at its minimum speed. So it's messy, there's a lot of algebra, but once I get there, you will be able to use that equation. You don't always have to derive it. So in the x direction, I've just isolated Fn equaling Fc over cosine theta minus mu cosine phi. I'm going to go do the same thing in the y direction. So in the y direction, we had my Fny, so this is Fn sine theta, plus my Ffy, this is Ff sine phi, equaling Fg. Fn sine theta plus frictional force equals mu Fn sine phi equaling Fg. Factoring out Fn, sine theta plus mu sine phi equals Fg. And again, isolating Fn all by itself, we get Fn equals Fg over sine theta plus mu sine phi. So two equations for normal force. Let's set those equal to each other. Fc over cosine theta minus mu cosine phi equals Fg over sine theta plus mu sine phi. One thing you will notice here is that the phi and the mu go with each other because remember phi went with friction. Friction equals mu Fn, so friction mu goes with the phi. So mu and phi will go together with these sines and cosines. I'm going to cross multiply and try and clean this up a little bit. You will notice that this is just messy. There's really no great way to do this. So cross multiplying, we get Fc times sine theta plus mu sine phi equals Fg cosine theta minus mu cosine phi. I want to get all of the sines and cosines on the same side, so I'm just going to divide. We get Fc equals Fg cosine theta minus mu cosine phi over sine theta plus mu sine phi. Fc equals mv squared over r. Fg equals mg. Cosine theta minus mu cosine phi over sine theta plus mu sine phi. M's cancel, so this is a common recurring theme. I'm going to bring r over to the other side. V squared equals Rg cosine theta plus mu cosine phi over sine theta, this is a minus, I'm sorry. This is cosine theta minus mu sine phi over sine theta plus mu sine phi. I'm going to rewrite this. Speed squared, and this is the minimum speed to safely navigate a banked curve with friction, equals Rg cosine theta minus mu cosine phi over sine theta plus mu sine phi. I realize this is a beast of an equation. This is not something that you have to derive. This is not something that you have to memorize. I will give you this equation for a test or a quiz. So yes, it was a long derivation. I wanted you to see where it came from. This is how you figure out the speed, minimum speed necessary for a car to safely navigate a banked curve with friction. There are 5 variables. You've got your speed, four variables: speed, radius, theta, and phi. So again, theta, phi, once you have one, you can get the other, 90 minus, and mu. You could be expected to solve for any one of those things. So either of the angles, mu, radius, or speed, and the practice problems will cover, I think, almost all of those. That was half of it. Let's now look at the maximum speed. This is going to go through a lot quicker just because the steps are very similar. It's just the direction of the friction that will change. So maximum speed around a bank curve. Force diagram. You've got your Fg, you've got your Fn. To safely navigate a turn and not go too fast. So if you go too fast, you're going to go flying up, which means your frictional force has to go down the incline. Going to break this apart the same exact way, breaking apart normal and frictional force. So Fnx, Fny, Ffx, and FFY. This angle is theta, that angle is phi. These two lines should be the same line, but just for the sake of space, I put those parallel to each other. FG plus FFY should equal my normal force in the y direction. So I have to shorten this a little bit. Okay. So from our force diagram, normal force in the y, top equals bottom, is equal to FFY plus FG, and a negative centripetal force is equal to right minus left, so 0 minus Fnx minus FFX. Because those are all in the same direction, those negatives all cancel out to a positive. Okay, I'm going to go a little bit quicker. Fny is Fn sine theta. This equals FFY, so FF sine phi plus Fg. Fn sine theta equals mu Fn sine phi plus Fg. Fn sine theta minus mu Fn sine phi equals Fg. Fn equals, I'm skipping steps here, factoring out the Fn and then dividing, we get Fn equals Fg over sine theta minus mu sine phi. That's in the y direction. Let's look at the x direction. Fc equals Fn cosine theta plus Ff cosine phi. So Fc equals Fn cosine theta plus mu Fn cosine phi. Again, skipping some steps, factoring out that n, because these are very similar steps to the last one. Fc over cosine theta plus mu cosine phi equals Fn. Okay, setting my two equations for norms equal to each other, we get Fg over sine theta minus mu sine phi equals Fc over cosine theta plus mu cosine phi. Cross multiplying, Fg cosine theta plus mu cosine phi equals Fc sine theta minus mu sine phi. Getting those sines and cosines to the same side and breaking apart Fg and Fc. So Fg equals mg times cosine theta plus mu cosine phi over sine theta minus mu sine phi equals Fc, which is mv squared over r. Once again, my m's cancel, bringing r to the other side. We get rg cosine theta plus mu cosine phi over sine theta minus mu sine phi equaling v squared. Just rewriting this again, this is for maximum speed around a banked curve. So Vmax squared equals Rg cosine theta plus mu cosine phi over sine theta minus mu sine phi. Again, this is an equation you will get, so I will give you the minimum speed and the maximum speed for navigating banked curves. I don't expect you to memorize it or know how to derive it, but it's there in case you're interested in how that derivation went. Okay, so here's our example. What is the maximum speed that a car may round a curve with a 17.5-degree bank and a radius of 32 meters if the coefficient of friction is 0.80? So that's rubber on dry pavement. And then we're going to look and see what this maximum speed is if the coefficient of friction is 0.30, so rubber on wet pavement. Again, for banked curves problems, all I really need to see is the diagram. So you've got your angle of 17.5 degrees for the bank. You want to show the car. This is the back of the car. And I need your give and find and then the force diagram. Our given information here, it tells us the angle of the bank is 17.5 degrees, so that's my phi. The radius is 32 meters. And then for part 1, it tells us that the coefficient of friction, mu, is 0.80. And then for part 2, mu is 0.30. And both parts are asking us to find maximum speed. So maximum speed, we already know what the equation is, and again, this is something that I will give you. Maximum speed around a bank curve is equal to Rg cosine theta plus mu cosine phi over sine theta minus mu sine phi. So for part A, using mu is 0.80, this equals the radius, 32 meters, times 9.8 meters per second squared, cosine of theta. So theta is 90 minus 17.5 degrees, so this is 72.5 degrees, plus mu, 0.8, cosine of phi, 17.5 degrees. And it's all of this over sine of 72.5 degrees minus 0.8 sine of 17.5 degrees. Biggest thing here is making sure that you put everything in your calculator correctly. I honestly recommend doing this in several parts just to make sure that you're not making a mistake by forgetting a parenthesis somewhere, instead of trying to put this whole big blob of numbers into the calculator at the same time. So once you do the calculation, you should get that v squared is equal to, and this is for the 0.8, so v squared equals 467.7, keeps on going, meters squared per second squared. Taking the square root of that, v max equals 21.62, keeps on going, meters per second. So with 2 sig figs, V max on dry pavement is about equal to 22 meters per second. And then part B is asking what if the coefficient of friction is 0.30, so that's rubber on wet pavement. So same equation, our maximum speed equals radius 32 meters times g 9.8 meters per second squared. Cosine, our angles are the same, so cosine of 72.5 degrees plus mu 0.3 cosine of 17.5 degrees all over sine of 72.5 degrees minus mu 0.3 sine of 17.5 degrees. And this will equal 213.11, keeps on going, meters squared per second squared, and that's my Vmax, it should be squared. Vmax squared, taking the square root, maximum speed on wet pavement equals 14.59, keeps on going, meters per second. So Vmax is approximately equal to 15 meters per second. And it makes sense that you need to go slower on wet pavement, so wet pavement versus dry pavement, because it's going to be a little bit more slippery. So that's how we solve bank curves. This was very basic, kind of a plug and chug once we got to the equation. Again, you're not expected to know how to derive. I did want you to see what the derivation looked like, and I will give you the max and the min equations. I'll do one more example. So I will do number 4, the one right after this, and then we'll work on the other ones in class as practice. If you don't care to see the other example, then fine. If you do want to see number 4 solved out, then keep watching. Number 4 tells us a race car is capable of traveling at 98 meters per second. If it goes around an 85-meter curve banked at 27 degrees, what must the coefficient of friction be? So race car is going around the curve. We need to show the diagram. Here's the angle banked at 27 degrees. Listing our given information. We know that the speed is 98 meters per second. The radius is 85 meters, and phi is equal to 27 degrees. 90 minus phi means that theta is equal to 63 degrees. And this time we are looking for mu. So force diagram. Going down we have Fg. Perpendicular to the surface is Fn. To keep it at maximum speed, remember we want to keep it from flying off, so our frictional force has to go down the incline. And then breaking this apart, we get Fny, Fnx, Ffx, and Ffy. And we just want to make Fg shorter so that top equals bottom added together. So there's my Fg. Angle theta is with the normal force, and my angle phi is with the frictional force. So we know that for maximum speed, Vmax squared equals Rg cosine theta plus mu cosine phi over sine theta minus mu sine phi. And here we're looking for mu. So we're going to need to do a bunch of algebra to get mu isolated. The first thing I'm going to do is get rid of the fraction and multiply both sides by the denominator. So v squared times sine theta minus mu sine phi equals Rg cosine theta plus mu cosine phi. I'm going to distribute this out, so we get v squared sine theta minus v squared mu sine phi equals Rg cosine theta plus Rg mu cosine phi. Okay, so I'm going to get all the mu's over to the same side, put everything else over to the other side. So let's move the mu's to the right. V squared sine theta minus Rg cosine theta equals Rg mu cosine phi plus V squared mu sine phi. Distributing out that mu, we get V squared sine theta minus Rg cosine theta equals mu Rg cosine phi plus V squared sine phi. Okay, dividing both sides by the mess on the right to get mu completely isolated. We get V squared sine theta minus Rg cosine theta over Rg cosine phi plus V squared sine phi equaling mu. And now we're ready to put in the numbers. So it tells us that the speed is 98 meters per second squared. Sine of theta, so 63 degrees, minus Rg, so 85 meters, times 9.8 meters per second squared, sine of phi. Phi was 27 degrees. Oops, this is not sine, sorry. Cosine theta. So cosine 63 degrees divided by r, 85 meters, g, 9.8 meters per second squared, cosine phi, 27 degrees, plus v squared, so 98 meters per second squared, sine phi, 27 degrees. This all equals mu. Again, it's going to be a mess in your calculator. I recommend not doing this all in one step. But multiplying, dividing, all this fun stuff, we're going to end up with 1.60, keeps on going. Remember, mu is unitless, so equals mu. This is one of the few times this year we'll see a mu greater than 1. 2 sig figs, mu is approximately 1.6. The reason it's greater than 1, this is a race car. It's going around a racetrack. You need an incredible amount of friction for these cars. So in this case, it does make sense that mu should be greater than 1. In other words, your frictional force will be greater than your normal force. So that's banked curves. We'll work on more practice problems in class tomorrow. And yeah, that's pretty much it.